first topic in this course is infinite sequences in series. Material of it is in chapter 10. Second topic, after we finish that, will be differential equations, and the third topic is Laplace transforms. This topic, the first one, is probably the most difficult one of the course, and that's why I want to do it early, so you have lots of time to digest the material for examination purposes. There are already 4 parts that we want to talk about in this chapter. Section 10.1, which is what I want to talk about today, is infinite sequence of numbers. 10.2 is infinite sequences of functions. Then we will talk about infinite series of numbers, and then finally, which is perhaps the biggest part of this topic, is infinite series of functions. Definition. By definition, an infinite sequence is a function, f of n, whose domain is the set of positive integers. For example, if f of n is equal to 1 over n cubed, the difference between this and what you've got in first year calculus when you talk about functions f of x, they're usually defined for an infinite number of possible values of x and some interval, which includes all of them. Sequences are different. They're only defined for positive integers. So the only values of n that you can put into the sequence of n equal to 1, n equal to 2, n equal to 3, and so on. You cannot plug in n equal to minus 1. You cannot plug in n is equal to 3.5. Only 1, 2, 3, 4, 5, 6, can be put in. So we've got an infinite number of numbers associated with this function. The word infinite here doesn't tell you anything about the numbers, it simply tells you there's an infinite number of them. For instance, if I put into here 1, I get f of 1 is equal to 1 over 1 cubed, which is 1. F of 2 is equal to 1 over 2 cubed, which is equal to 1 over 8, and so on. I want the millionth term, I could plug in n equal to 1,000,000, billion, any positive integer I could plug it into this sequence. We often write in general that if I got this sequence f of n, then there's coming from it the first number when you plug in 1. Then you can plug in 2, and you can plug in 3, and so on, and so on, and so on. What I didn't mention is when you write these 3 dots, it's called an ellipsis, and that means continuing on forever. Right? What we call this is the first term of the sequence. And similarly, this is the second term. And I put out here comma, and I write f of n, and comma, another ellipsis. This would be called the nth term. Now I should mention that you don't have to have the domain of this function being the positive integers. In some texts you'd find out that you could start it anywhere you want. I could start by saying a sequence is a set of numbers that you get by plugging values of n which are larger than or equal to 100 or minus 5. There's an advantage, however, of starting with n equal to 1. Advantage is, if you want the millionth term of this sequence, all I have to do is put in here n equal 1,000,000, because the first term corresponds to n equal to 1, the second term to 2, the third term to 3. If you say I'm going to start numbering at 1,500,000, or 1,000,000, say 500,000, then you got a bit of a problem. You want the 100th term, then you got to say, now I got to figure out what value of n I should substitute. This is what advantage of start with n equal 1. We're not always going to do that. When it comes to infinite series of functions later on, it will be advantageous to start with n equal to 0 rather than n equal to 1. But that's later. Mathematicians don't like writing a lot, so instead of writing this, what we would often write is simply c sub 1, saying c standing for constant or number, and that's the first term. Then c sub 2, the second term, c sub 3, and so on, up to the nth term, and then carrying on forever. Little less writing to do. We would shorten that even further. They would write the following, curly brackets, c sub n, like that. Some books would put on 1 and infinity to indicate that the first value of n that you substitute is n equal to 1. Infinity says n you go on forever. I won't write this unless there's a necessity to do so. I will simply drop that off and we will understand that when you see curly brackets, you see a function of n in here, it means you're talking about a sequence, and that nth term in there, that function of n in there is actually a sequence. We don't actually, most times, talk about the function we receive. We call this list the sequence rather than the function from which it came. Slight misuse of language, but it's common to do so. So this is the sequence. In here is actually the formula that gets you the terms in the sequence, right? So all of that is notation. Let's take a look at some examples that I want to come back to later. And we'll calculate a few terms just to get the idea. Suppose that f of n is equal to, want some specific ones, 1 over 2 to the n. So this is the sequence. We read out the terms. We also call that the sequence. The first term you get is by substituting n equal to 1. So the first term is 1/2. The second term, you substitute 2, you get 1 over 4. Third term, 1 over 8, and so on and so on. Relatively straightforward. Suppose I say a second example, let's call this example 1. Example 2, so let's use the other notation, say 1 over n cubed. I want a different one, let's not put it in the bottom. N cubed. So we say, all right, terms in this sequence, we don't call them C, we just write them out. First term, you substitute 1, you get 1. Then you put n equal to 2, you get 8. You put n equal to 3, you get 27, and so on and so on. So there's the first 3 terms of that sequence. Next one, example 3. Sequence -1 to the n plus 1. First term, substitute n equal 1, get -1 squared, 1. Second term, substitute n equal to 2, get -1 cubed, -1. And then back to 1, -1, and so on and so on. There are lots of properties that one talks about sequences. Most of them we won't get into, only one, which will come up maybe this class or maybe the next one. For instance, in this first sequence, you can see that the terms are getting smaller and smaller and smaller. And they do so forever. The second sequence, you can see that the terms are getting bigger, 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 bigger. Third one, not so. Big, small, big, small, big, small, big, small. This is what actually we call it. Decreasing sequence, an increasing sequence, and an oscillating sequence, but you don't have to know about that terminology. Last one I want to look at is, suppose we have n over 2n plus 1. We write out a few terms. First term, substitute n equal to 1, get 1 over 3. Next term, substitute 2, 2 over 5. Next term, 3 over 7. Next term, 4 over 9, and so on and so on. Right? So there's a few term or sequences, calculated a few terms. That's relatively simple to do. And again, if you want the millionth term in this sequence, you simply put in n equal to 1,000,000. You want the 100th term of this sequence, you put in n equal to 100. Relatively straightforward to calculate terms of a sequence. We say that these sequences are defined explicitly. That is, what you actually have, you've got a formula for the nth term of the sequence. The formula in this sequence is this one. Formula for this sequence, that. Formula for this sequence, that, and so on. And that makes it relatively easy for explicit sequences to calculate terms. There's another way to define sequences. We won't have a lot to do with them, but in practice, they turn out to be very, very important. Time just doesn't permit us to discuss them in detail. So let me call this one example 5, and I'll write the following on the board. C sub 1 is equal to 2. I tell you that the first term in the sequence is 2. And then I write this. C sub n plus 1 is equal to 3 plus the square root of 5 plus C sub n. And I say n greater than or equal to 1. This is called a recursively defined sequence. To get the terms, you just do what is suggested here. If you want the second term, that would be C sub 2. You simply take this formula and you put in n equal to 1. So we do that, we get C sub 2 is equal to 3 plus the square root of 5 plus C sub 1. But we know what C sub 1 is, it is 2. So the second term is 3 plus the square root of 5 plus 2. Therefore, 3 plus the square root of 7. So there's the second term. You want the third term, you take this recursive definition, and now you substitute n equal to 2. That will give C sub 3. So you get 3 plus the square root of 5 plus C sub 2. But we just calculated C sub 2 to be this. So we'll have 3 plus the square root of 5 plus this one, 3, the square root of 7, so you get 3 plus the square root of 8 plus the square root of 7. You can see one huge disadvantage of a recursive sequence. Suppose for this example that I wanted the 100th term. It's not like these sequences where you simply say substitute n equal 100. You want the 100th term in this sequence, you have to know the 99th in order to get it. To get the 99th, you need the 98th, and so on, and so on, and so on. So if I want the 100th term in this sequence, I have to calculate the first 99 terms in order to get the 100th term. Not particularly nice. Okay, if I had a program on my machine, a calculator, or a computer, I could tell it to do that very quickly. But for me to do it by hand, that would be unbelievably laborious. One question that would arise then is, could you or can you turn a recursive definition into an explicit one? The answer is not likely. There's the odd few that we can do that. They have to have special nature. For instance, if I were to remove this square root, like that I would combine the 3 and the 5, that one, having then 8 plus C sub n, that one I could find an explicit definition. For this one, I can't. It can be very difficult to go from a recursive definition to an explicit one. As I said, these recursive sequences are very important in applications. I'm not sure whether you took Newton's method for solving or approximating solution equation in first year. If you did, therein you saw recursive definition of a sequence. Almost all numerical procedures have recursive aspect to them. What we've seen here so far is that if I give you the formula for a sequence, it's very easy, except for the recursive kind, to calculate any number of terms of that sequence that you want. Suppose I turn it around and I give you some terms of a sequence and ask you, can you find an explicit formula for the rest of the terms? For example, suppose I put up here was 4, that was 5, so this had better be 6. Suppose I write 4, 6, 8, 10, dot, dot, dot. Now, don't get the idea that if I give you 4 terms of a sequence, that there's only one sequence that has those first 4 terms. I could make up an infinite number of sequences that have these as the first 4 terms. But what we want to come up with is perhaps what we might call the simplest one. All right, so let's think about it. What you want, and often a good idea, is to write above the terms the value of n that is giving them. That is kind of much easier to see what the formula would be. So that if you put in n equal 1, you get 4. If you put in n equal 2, you get 6. If you put in n equal 3, you get 8. Put in n equal 4, you get 10. I'll give you 10 seconds and see if you can write down a formula that would do that. The key is that these ones go up by 2. Once you see the terms increasing by 2, don't write n plus 2. Lots of people try that, but that doesn't work. If you take that and you increase n by 1, then that number does not go up by 2, it only goes up by 1. So you don't want to put a plus 2, what you want to put is 2n. But, if you look at it, you increase n by 1 there, then that quantity increases by 2. But that doesn't quite work, because if I put in here n equal to 2, I get, or n equal to 1, I get 2, I don't get 4. If I put in n equal to 2, I get 4, I don't get 6. But I think you can see that if you add 2, then you get a formula that works. So this would be a sequence. This would be a formula for a sequence that gives rise to these first 4 terms. Perhaps the simplest one that we can think of. Second example. Example number 7. 1.4, and by this dot I mean multiply, it's not a decimal dot, over 2. Next term, 3.7 over 5. Next term, 7.10 over 10. Next one, 15.13, I think I got it written down here, over 17, and so on. In an example like this, what you should do is not look at the whole thing, look at the parts, look at the denominators, then look at the 1, 3, 7, 15, then look at the 4, 7, 10, 13, look at those separately and figure out separate formulas for each of those parts and then put them together. So let's see if we can do that. Well, if we look at, let's look at the 4, 7, 10, 13. That's somewhat like the first example. They go up by 3. Each term, and the term goes up by 3, so probably we should write 3n. But that doesn't quite work. Again, probably a good idea to put n equal 1, n equal to 2, n equal to 3, n equal to 4. If I put n equal to 1 in there, I get 3, I don't get 4. But if I were to add 1, then I would get it. Let's check and make sure it works for here. Put in n equal 2, yes, I get 7. Put in n equal 3, I get 10. N equal 4, I get 13. That looks good. So that takes care of it. 4, 7, 10, 13. All right. Let's look at the other part of the numerator. The 1, the 3, the 7, the 15. It's not like the other part. They don't go by the same amount, but think about those numbers, or think about numbers that are very close to them, that you would recognize a pattern for. And what I would suggest is, what if you were to add 1 to that, 1 to that, 1 to that, 1 to that? What would you get? You get 2, 4, 8, 16. Recognize those? Those are powers of 2. So in other words, I think what we need here is a 2 to the n, but we added 1 to get these, so let's take it off. So I believe that will take care of the 1, the 3, the 7, and the 15. 2 parts down, 1 to go. Let's look at the denominators. 2, 5, 10, 17. Again, they don't go up. The difference here is 3, the difference is 5, the difference is 7. Ooh. I wonder if the difference in the next one is 9. I don't know whether I could use that anyway, even though it's true. If their differences are the same, it's clear what I do. When they're different like that, even though there's a pattern there, I'm not sure I can think about how to handle it. Oh, but let's use the idea of what we did these ones. What if you were to subtract 1 from every one of those? If you did, you get 1, 4, 9, 16. What are they? Those are squares. So how about then having n squared to get these, but we have to add back on the 1 to get these ones. How does that work? So there would be then an explicit formula for the terms of that sequence, perhaps the easiest one that we can come up with. Again, I could make you up a million more. For instance, suppose, just as an aside, suppose I were to put right there the following thing. n minus 1, multiply. n minus 2, n minus 3, n minus 4. All right? Let me get a plus sign. What if I put in n equal to 1? Do I still get this? Yes, I do, because that is equal to 0. If I put n equal to 2, do I still get this? Yes, I do, because that one's 0. n equal to 3, that one is 0. n equal to 4, that one is 0. But if I put in n equal to 5, we'll write down here what we wanted, which would be this one with n equal to 5, and you put n equal to 5 in here, you don't get 0, so it's different. So there would be a formula that has the same first 4 terms, but all the rest would be different than the one that we chose. All right? But we said we would come up with the simplest one, and why would I do something like that when I could come up with something simpler? All right. This one, example number 8. The sequence is 1, 0, 1, 0, 1, 0, on and on and on forever. Think about that for a few seconds. If you look back at your notes, if you're taking notes, or think about what we said earlier, the key is one of the sequences that we already saw. Remember this sequence? Minus 1 to the n plus 1. What did it do? It was 1, minus 1, 1, minus 1, and so on. This one you can use to get a formula for that one. Question is how? Answer. Suppose you were to take to this sequence and add 1 to make a new sequence. These guys would then turn into 2 and 0, 2 and 0, on and on and on forever. You want that one, so take this one, divide all the terms by 2. So the formula for this sequence then would be 1/2. 1 plus minus 1 to the n plus 1. That one, right? If you want a challenge, See if you can come up with a formula for the sequence that's 1, 1, minus 1, minus 1, 1, 1, minus 1, minus 1, and on forever. See if you can come up with a formula for that one. I'll give you a hint. Think trig. I'll leave that one with you, or something for you to play with. One last one I want to write down. A little more difficult than these ones, but precisely the kind of scenario that we're going to be seeing over and over again when it comes to infinite series of functions. So what I want to write down then, and this is example number 9. First term of the sequence is 2x. Next term is minus 4, x to the 5th over 1.3. The next one is 8, x to the 9th over 1.3.5. The next one is minus 16, x to the 13th over 1.3.5.7, and again, those are multiplies. As I said, you will be finding explicit formulas for sequences that look like this over and over and over again when it comes to infinite series of functions. I like, especially in these kinds, to put my n values on top. Help me see patterns. Let's do this one the same kind of way that we did this one. Look at the individual parts and then put them all together in a minute. Equals. Formula going to go into here. All right. The fact that they go positive, negative, positive, negative, positive, negative, the key is this guy here. This guy went 1, minus 1, 1, minus 1. This was going 1, positive, negative, positive, negative. Should we therefore write minus 1 to the n plus 1? That will take care of the positive, negative part. All right. The 2, the 4, the 8, and the 16, we've already seen that one. Those are powers of 2. So we could write 2 to the n. Then we've got powers on axis. What do? They go up by 4. Went from 1, 5, 9, 13. That means we should have a 4n. That doesn't quite work, right? We want, when we put an n equal to 1, we want to get power 1. This is going to give 4. What if we subtracted 3? That would work. Doesn't work on this one. If I put an n equal to 2, what do I get? 5. N equal to 3 gets 9. Good. Working nicely. Now the bottom. Well, you'll recognize the bottom. Those are odd integers. All right? The key is, and the problem often is, what people will do is they'll figure out a formula for the last one, and they'll simply write that expression down, and that's it. But that's not the way it is. You've got to take all of these things, 1.3.5.7, ... up until you get to the last one. Since they go up by 2, there must be a 2n in here. If I put an n equal to 1, or let's look up this one, or let's look up this one. If I put an n equal to 3, I'm supposed to get 5. If I put an n equal to 3, I get 6. Oh, I think that means I probably should subtract 1. Let's check out this one. Put an n equal to 2, you get 3. Check out this one. You put an n equal to 4, that's it. So there it is. There's a formula, explicit formula for the terms in the sequence above it. A little more complicated. This one can be simplified, and later on I will want you to do that. This thing I just don't like. Question is, could I simplify? Answer is yes. Let's go off to the side, look at it, and then when I've got it simplified, I'll bring it back and put the simplification into here. So I don't have to keep writing all this other stuff from the top down over and over again. Let's just work on what I want. This is not a factorial. Some people call this a non factorial and make up a special notation, something like this. I personally don't like it, so don't use it. If the even ones were there, then it would be a factorial. So let's put the even ones in. If I put the even ones in, I'd have 1, 2, 3, 4, 5, dot, 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 up to 2n minus 1. And I could fill into here, and what's in there? Do you agree what's in there is 2n minus 2? Let's put it there. And then we got the 2n minus 1. I'm going to put on one more, not for an obvious reason now, but it will become clear when we do the infinite series of functions later. I'm going to put on the next even one, which is 2. Now I put an equals here. No stretch of the imagination. Is this equal to this? I put a whole bunch of even numbers in there. But if I put those same numbers on the bottom, now they're equal. The top I can run as a factorial. All right. But you might say, well, that's great. Simplified the top, but you made the bottom just as bad as it was before. But the bottom, all of these numbers are even. So how do I take and pull out of here 1, 2, pull out of here one of the 2's, pull out of here one of the 2's, out of every one of these terms, pull out a 2. That means for this one I'm thinking 2.1, for this one I'm thinking 2.2, for this one I'm thinking 2.3, this one I'm thinking 2.n. Now remember, all of these things are multiplied together. So I'm going to pull out that 2, that 2, that 2, and that 2. Right? It's not a common factor. Because these things are multiplied. How many 2's did I just circle? Answer, n of them. So if I pull out the 2's, that's 2 to the n. And what's left? 1, 2, 3, up to n. Well, that's a factorial. So you can see that I can replace this with that, and there are no dot, dot, dots. So the final answer here is that we simply, instead of that thing, we substitute this. Minus 1 to the n plus 1, 2 to the n, x to the 4n minus 3, all over 2n factorial, over 2 to the n factorial. And then probably what you would do is say, these ones and these ones, since this is in the denominator of the denominator, it comes to the numerator, so the rest of that 2n. And this one I could put here, so I don't have it. So there. So there would be what I would consider the simplest possible expression representing the terms in this sequence. A little more complicated those over there because we've got x's in here as well as numbers. But again, this is going to happen over and over and over again later. You can draw graphs of sequences. And I did so for 4 sequences in the book. I'm not going to do it here because I don't normally find it particularly enlightening to draw a graph of a sequence. It's a bunch of dots. Instead of a curve, it's a bunch of dots. Let's do one. All right? Let's do one. Suppose I gave you the sequence 1 over n. I say, let's draw its graph. So you draw an n-axis, and you draw a Cn axis or an f of n axis. You see, all you're going to substitute into this sequence are the positive integers. You put in n equal to 1, and you get 1. So that's 1. You put in n equal 2, you get put in n equal 3, you get a third, you get a quarter, and so on and so on. So there's a graph of that sequence. A bunch of dots, one on top of every positive integer along the n-axis. Right. As I mentioned, there are lots of properties of sequences that are important in some applications, and many of them are dealt with in section 10.8, but you're not responsible for that. Things like increasing sequences, decreasing sequences, non-increasing, non-decreasing, right? Upper bounds, lower bounds, least upper bounds, lowest upper bound, least, greatest lower bound, all of these, but we're not concerned with those. All we're interested in talking about are limits of sequences. It's the only thing that we want to talk about. You recall in calculus that they gave you a function out of x. Say x cubed plus 2 over x plus 5. You can talk about taking the limit of that function as x approaches basically anything you want. You could let x approach 1 and talk about limit as x approaches 1. Limit as x goes to infinity, minus 5, plus 5, minus 10, right? For sequences, that's not true. For sequences, there's only one kind of limit that you can talk about. You can't talk about giving, say, this sequence here. You cannot say, what is the limit as n approaches 3 of 1 over n? You can't ask that question. It doesn't make sense. Because by a limit, you mean let n get closer and closer and closer and closer to 3 and watch 1 over n. But n can't get closer and closer and closer to 3. Closest it can get is 2 and 4. So limits of that type don't make sense. The only limit you talk about for a sequence is the limit as n goes to infinity of a sequence. And what you're saying is, watch the terms in the sequence and ask, do they get closer and closer and closer to anything as n gets larger and larger and larger and larger? Do they get close to something and stay close to it? Let's examine some of the simple ones that we already saw, right? If a limit exists, what do I say? L might stand for limit. Next day we'll deal with some more difficult ones. First example we saw, limit as n goes to infinity was 1 over 2. That was the first stage sequence that we looked at. Is it clear to you that as n gets larger and larger and larger, the denominator gets larger and larger and larger, and therefore this limit is 0. That the terms of that sequence get closer and closer and closer to 0. Second one I looked at was the limit as n goes to infinity. I looked at was n cubed. We saw that one. Does that one have a limit? If I look at the terms, they get closer and closer and closer and closer to something as n gets bigger and bigger and bigger. The answer is no. And cube gets bigger and bigger and bigger. So this one, we would say, does not exist, but it's better to write infinity, just like you did in first year calculus, the same idea. Infinity means does not exist. Reason is, terms are getting huge, and they don't stop getting huge. All right? Next one we looked at was the limit, or was the sequence, minus 1 to the n plus 1. Limit, n go to infinity, minus 1 to the n plus 1. Does that sequence have a limit? Remember the terms were 1, minus 1, 1, minus 1, 1, minus 1. Are the terms getting closer and closer to anything? No. So this one we would write does not exist, but we certainly would not write the infinity. All right? So there's various ways that a sequence cannot have a limit. One is the terms get huge. This one is they just don't settle down and approach anything. And one last one that we looked at earlier was n over 2n plus 1. We wrote out a few terms, and if we were to write out a few more terms, we might be able to kind of see or guess what the limit is. But you had Church in first year for doing that kind of limit. Recall what it would mean. The answer was, if you divide top and bottom of this term by n, you get 1 on the top, you get 2 plus 1 over n. So dividing that by n and dividing that by n gives you that. That does make it clear. As n gets huge, This goes to 0, so the limit of the sequence is 1/2. So there are some obvious ones. We'll consider some not so obvious ones next day.